everyone, welcome back to my channel. I'm Preeti, a second year computer science and engineering student at Venkateshwara College of Engineering, Bengaluru. In today's video, we'll be discussing about one-way ANOVA. The table of contents of this video are Introduction to ANOVA, Null and Alternative Hypothesis, Assumption of one-way ANOVA, Calculating the test statistic, Interpreting the F ratio, Post-hoc analysis, Multiple comparisons, Effect size and statistical power, ANOVA in practice, examples and case studies, limitations and considerations, and conclusion. One-way ANOVA. One-way analysis of variance, that is, one-way ANOVA is a powerful statistical technique used to determine if there are significant differences between the means of three or more independent groups. This fundamental tool in the field of experimental research allows researchers to uncover the underlying patterns and relationships within the data, providing valuable insights that can drive informed decision making. By delving into the nuances of one-way ANOVA, this presentation will equip you with the knowledge to effectively leverage this analytical approach in your own work. Introduction to ANOVA. So first let's see what is ANOVA. ANOVA is a statistical method used to compare the means of two or more groups to determine if they are significantly different from one another. It is an extension of the t-test, allowing for the analysis of more than two groups simultaneously. Types of ANOVA. The main types of ANOVA include one-way ANOVA, two-way ANOVA, and repeated measures ANOVA. Each type is tailored to address specific research questions and experimental designs. Applications of ANOVA. ANOVA is widely used in various fields such as psychology, biology, education, and business to compare group means and identify significant differences in experimental or observational data. Now let's see null and alternative hypothesis. Null hypothesis, it is denoted by H naught. The null hypothesis states that there is no significant difference between the means of the groups being compared. It represents the assumption of no effect or no difference. Alternative hypothesis, it is denoted by H1. The alternative hypothesis suggests that there is a significant difference between the means of at least two of the groups being compared. It represents the research hypothesis that the investigator wants to test. Hypothesis testing. The one-way ANOVA procedure tests the null hypothesis by calculating a test statistic and comparing it to a critical value. The decision to reject or fail to reject the null hypothesis is based on the p-value obtained from the analysis. Assumptions of one-way ANOVA. Here we'll be discussing about independence, normality, homogeneity of variance, and absence of multicollinearity. Independence. The observations within each group must be independent of one another, meaning that the score of the one participant does not depend on the score of the another participant in the same group. Normality. The dependent variable must be normally distributed within each group. This assumption can be checked using statistical tests or visual inspections of the data. Homogeneity of variance. The variance of the dependent variable must be equal across all groups. This assumption can be tested using Leven's test or Bartlett's test. Absence of multicollinearity. In the case of factorial ANOVA, the independent variables must not be highly correlated with each other, which could lead to issues with interpretation. Calculating the test statistic. This includes three steps. Step 1. Calculate the total sum of squares. The total sum of squares represents the total variability in the dependent variable, considering all observations across all groups. Step 2. Calculate the between group sum of squares. The between groups sum of squares reflects the variability in the dependent variable that is explained by the differences between the group means. Step 3. Calculate the within group sum of squares. The within group sum of squares represents the variability in the dependent variable that is not explained by the group differences, but rather by the individual differences within each group. Now let's see the topic interpreting the F ratio. The F ratio. The F ratio is a test statistic used in one-way ANOVA, calculated as the ratio of the between groups variance to the within groups variance. It represents the strength of the effect of the independent variable on the dependent variable. Statistical significance. The F ratio is compared to a critical value from the F distribution based on the degrees of freedom for the between groups and within groups variance. If the F ratio exceeds the critical value, the null hypothesis is rejected, indicating that there is a significant difference between the group means. Effect size. The effect size, as measured the partial eta squared statistic, provides an estimate of the proportion of the total variance in the dependent variable that is explained by the independent variable. Post-hoc analysis, multiple comparisons. The first one is identifying significant differences. If the one-way Anova reveals a significant overall effect, post-hoc tests such as two-case honesty significant difference or Bonferroni corrections are used to determine which specific group means differ significantly from one another. Second one is adjusting for multiple comparisons. Post hoc tests adjust the significance level to account for the increased risk of type 1 errors, that is, false positives, when conducting multiple pairwise comparisons. This ensures that the overall type 1 error rate is maintained at the desired level. And third one is interpreting the post hoc results. The post hoc analysis provides a more detailed understanding of the group differences, allowing researchers to pinpoint which specific groups differ significantly from each other and the magnitude of those differences. Effect size and statistical power. Effect size. Effect size measures the magnitude of the difference between the group means, providing a standardized measure of the strength of the effect. Common effect size measures include cohency and partial eta squared. Statistical power. Statistical power is the likelihood of detecting a significant effect if one truly exists in the population. A priori power analysis can help determine the appropriate sample size to achieve the desired level of statistical power. Interpreting effect size and power. Reporting both the effect size and statistical power provides a comprehensive understanding of the practical significance and the reliability of the findings, allowing for more meaningful interpretation and applications of results. Anova in practice, examples and case studies. Educational research. Comparing the effectiveness of different teaching methods on student learning outcomes. Medical research. Investigating the effects of various drug treatments on the recovery rates of patients. Marketing research. Analyzing the impact of different advertising campaigns on consumer purchasing behavior. Psychological research. Examining the differences in personality traits across diverse cultural backgrounds. Now let's see the limitations and considerations. The first one is assumption violations. When the assumptions of one-way ANOVA are violated, such as non-normality or unequal variances, the validity of the results may be compromised. Appropriate remedies like data transformations or non-parametric alternatives should be considered. Confounding variables. One-way ANOVA only examines the effect of a single independent variable on the dependent variable. If there are other factors that may influence the outcome, they should be accounted for in the study design or through the use of more complex ANOVA models. Interpretation caution. While one-way ANOVA can identify significant differences between group means, it does not provide information about the specific nature or direction of those differences. Post hoc tests and effect size measures are crucial for a more nuanced interpretation. Now, let's have a conclusion for today's session. In summary, ANOVA, that is analysis of variance, is a powerful statistical tool for comparing means across multiple groups, helping researchers determine if observed differences are statistically significant. By testing hypotheses and interpreting the F ratio, we gain insights into the relationships between variables. Post hoc analysis provides further clarity on specific group differences, while effect size and statistical power ensure our results are meaningful. However, it's crucial to remember ANOVA's assumptions and limitations. Misinterpretation or violation of these assumptions can lead to inaccurate conclusions. When applied thoughtfully, ANOVA remains an essential method in research, offering valuable insights across disciplines. Thank you for watching. Please do like and share the video.